Hey, welcome everybody to DesignSafe. This is probably the fourth webinar we've done in 2021 and getting rather good at doing all these Zoom meetings. I hope you guys are enjoying it. So welcome. Today, we actually have a really cool thing in line for y'all. We have the first winners of our data awards from DesignSafe who are going to be giving their talk today. So if you have any questions or anything, or any other suggestions about our webinar series, feel free to email me. My email's on the slide, charlie@tac.utexas.edu. And if you have any suggestions or some feedback, we would really appreciate it. You can scan the QR code on your screen with your phone. And that will take you to a survey. You'll also be emailed a link to that survey as well. If you haven't taken it, please do. This helps us plan better webinars in the future, take interest in your interests, and build a stronger community. So we really appreciate your feedback with our DesignSafe surveys. So with that, let me introduce the topic for today's webinar. So we're doing a look at the data set of lightly reinforced concrete wall testing. It was essentially experience that New Zealand researchers had, and then how they published their information to DesignSafe. So essentially, in the last decades, the research work for earthquake engineering has just grown tenfold. And this is a data set of slightly reinforced walls on multi-story buildings that has been collected and studied and researched on DesignSafe, and has given, essentially had given birth to the New Zealand structure codes and the US building codes for structural concrete. And so all these data points were recorded and documented. And we have two of the researchers involved in that project going to be presenting their work today. Rick Henry from the University of Auckland and Yuki from the Zurich in China. So our speakers is Rick Henry, is a senior lecturer at the Department of Civil Engineering, Civil and Environmental Engineering at the University of Auckland. His research includes seismic design and assessment of reinforced concrete structures, concrete wall design and repairability, and precast concrete construction and low damage vision. He's also an associate investigator with QuakeCore, which is New Zealand's Center for Earthquake Resilience, and the lead for QuakeCore Technology Platform 1 large-scale laboratory facilities. Our other speaker today is Yuke Liu. He's a chief structural engineer in Zurich from China. He's the leading research project in seismic performance of buildings using intelligent construction technologies. And he received his PhD in civil engineering from the University of Auckland and worked as a research fellow at the same institute for 3 years. So they're going to be presenting their data sets with us and how they've been able to implement DesignSafe into their research. So with that, let me stop my share and I'll hand it off to you. Thank you very much for joining us this afternoon, and I'm looking forward to your talk.
Excellent. Well, thanks very much for the introduction, and it's a pleasure to be able to present this today, and joining sort of myself in New Zealand, Ichu in China, and then those in the US as well. And so this is really about the data set, but more generally perhaps about some of our experiences in terms of trying to collect and archive these types of data and using DesignSafe for that purpose. So just a bit of an outline of what we'll go through. Some of the things are just a bit around the tests in terms of why we were doing these tests in the first place. And then Ichu's going to talk a bit more about the data set itself and how that's organized. And then sort of thinking a bit more around why we're particularly interested in publishing these data sets, and perhaps what some of the other data sets that we've published that are sort of related, and where we've been learning a bit about this sort of process as well. So many people would be quite familiar with the fact that around about 10 years ago now, we had a pretty significant series of earthquakes that we refer to as the Canterbury earthquake sequence. And it's really quite an unusual sequence that lasted almost 2 years with a number of quite major earthquakes that were located within the Canterbury region of New Zealand, which you see in a sort of diagram here, a map of the country where we sit on sort of a pretty active fault line. And Christchurch in the Canterbury region was where these earthquakes were really centered around, and a number of events that caused quite a bit of damage and ongoing sort of disruption through the Canterbury region. The most significant earthquake in terms of intensity was in February 2011, and we refer to that as the Christchurch earthquake. And this sort of shows just general spectra from measured accelerations in the central CBD area of Christchurch. And it was a really quite close earthquake to Christchurch under the Port Hills, about 20 kilometres from the downtown area. And so it resulted in really quite high intensity, but extremely short duration. So it's quite a difficult sort of earthquake to assess in terms of sort of relative to the design hazard, which was quite different for Christchurch at the time. And we saw quite significant damage to our older buildings, which we perhaps weren't too surprised at. So a lot of unreinforced masonry and older sort of concrete buildings were heavily damaged. We also had quite significant liquefaction and a lot of ground damage. So quite a lot of the damage outside of the CBD and in the residential areas was more due to the land damage. But generally, when we look at modern buildings, they performed relatively well. And with the exception of 2 buildings that collapsed and caused loss of life in concrete structures, the majority of our more modern buildings performed reasonably well. And so looking at the sort of lessons, we reflected that really as structural engineers, we initially thought the outcome looked pretty good. The sort of ductile capacity design approach that we'd been using since about the 1970s for our multi-storey buildings really worked the way it was intended. And so you can see here, typical sort of beam plastic hinging where we were getting the strong column, weak beam type action. And so that was sort of what was expected in these sort of moment frame concrete buildings. But really the sort of subsequent events after that made us realize that perhaps structural engineers hadn't communicated that very well to the general public. And so they were a bit surprised at the level of damage we thought was acceptable. But also really what we thought was repairable from a structural perspective turned out not to be repairable when we considered all of the other factors, particularly things like insurance and damage to non-structural components and the cost of repair. So it was really quite a big lesson in terms of repairability. One of the outcomes of that is that when they've rebuilt the city and they essentially demolished about 60 to 80% of the buildings in the Christchurch downtown area and rebuilt them, the designs that have been rebuilt are quite different and really a large use of stiffer type building systems rather than the flexible frames. So a lot of concrete walls or braced frames. And so there's been a lot more attention placed on wall behavior. When we look at the actual performance of concrete walls in the Canterbury earthquake sequence, we find a bit of a mixed bag of results. And so we have everything from walls that behaved almost exactly like you expect in the lab. So a couple of photos on the left there show really well distributed cracking and quite good plastic hinge behavior in some of these multi-storey walls. Whereas the other 4 photos show some perhaps less desirable failure modes and unexpected damage due to some different poor detailing practices and things that could be improved. And so really that led to quite a coordinated research program in New Zealand and collaborating with a number of people overseas as well around trying to look at these concrete walls and improve the design provisions so that what we were rebuilding was really going to be a good outcome in terms of future earthquakes. And so there were many aspects of walls that were perhaps critical or had research needs and impacts on our standards after those earthquakes. But the one that sort of is a focus of this particular research is around these lightly reinforced walls. And so this is a feature of Christchurch and other areas around New Zealand where the seismicity is a bit lower, and we sometimes have wall buildings where they've probably got more walls than they require for strength, and so they actually have quite low reinforcement ratios. A lot of precast concrete construction as well. And so this gives you a sort of typical example of one of the buildings that we were concerned about, where it's a multi-storey sort of apartment building with precast concrete walls on the outside, providing lateral resistance. And sort of engineer doing the inspection on this was a bit concerned that for a rather slender building where you'd expect some distributed cracking in a plastic hinge region, there was just a single crack at the base of the wall. And sort of doing some quick maths, sort of thought that didn't make sense in terms of good response. So they investigated with some destructive sort of intrusive investigation, breaking out some of the concrete around the base of the wall to see what was underneath that crack. And what they found was pretty disturbing. The reinforcement you can see in here is actually fractured, sort of extended, necked, fractured, and then gone back and closed up again. And so the crack had opened, had fractured all of the reinforcing along the whole length of the wall, and then gone and sat back down and closed up again. And so it was really quite concerning in terms of this hidden damage, and attributed to this sort of type of lightly reinforced walls. So it really led to us focusing our research around this topic, and in particular focusing on how we control this in the design of new buildings, and the fact that if we really want to get good distributed cracking in the plastic hinge region, then we need to make sure we're putting an appropriate amount of reinforcement to actually ensure we get that, and across different sort of ductility requirements for walls, that we understand what design requirements are necessary. So it was all about getting good distribution of cracking, rather than getting a concentration of cracks at one or two locations where we got strains in the bar that were concentrated and therefore led to premature fracture and other problems as well. And so it was really the motivation behind this, and trying to understand the wall performance so that we could then inform our design practice. So I'll hand over to Ichu, and he's going to go through some of the test wall and data set.
All right. Okay, thanks, Rick. Let me share my screen. All right, so in next 25 minutes, I'm probably going to focus on the data set. So Rick has talked about the background of the research. We have done this 11 wall test and have published in the DesignSafe. We also have a companion paper published recently in Journal of Structural Engineering, where in this paper we have described the data collection process and the data structure in DesignSafe. So after the presentation, if anyone interested in this paper, have more details about the data set as well. And in today's presentation, I will also focus on these two parts. What's the data inside in the data set, and what is the structure in the DesignSafe? So this research program is one part of my PhD topic, actually. So before I started this research program, I was trying to find some walls, some previous test walls that have similar, similar detailings, where we are interested in of the walls. So trying to find these walls, so I collected a database on the previous RC wall testing. And my focus is on the lightly reinforced concrete walls where the reinforcement ratio is below 1.0%. When I'm looking at these walls, actually, they do have quite a few walls on the lightly reinforced concrete wall test. But when I look at into details, most of the previous testing lightly reinforced concrete walls have low shear span ratio, where they focus on the shear behavior of the walls. And they also do have some flexure-dominant, but at the end region, they always put lots of lumped reinforcement ratio and extremely low reinforcement ratio in the wall web, which also cannot represent our walls we are interested in. And these walls have pretty high axial load, which also cannot represent the normal walls with minimum requirements. So the walls that we are interested in with high axial load ratio, with high aspect ratio, with flexure-dominant, minimum vertical reinforcement, and a low moderate axial loads. There's quite a few tests on them. So to address the test data of this lightly reinforced concrete walls, we did the research X program. So basically, the research X program can be separated into two phases. In the first phase, we did a 6 C walls. C means current. So this 6 walls represent the current minimum requirements in accordance with the New Zealand code at that time. So after we did this test and based on the test results, New Zealand code have changed their requirements of minimum reinforcement ratio. So we did another 5 walls, M walls. M means modified to verify the behavior of this M walls. So in these walls, they require both lumped reinforcement ratio at the wall end and also wave reinforcement ratio as well. So in total, in our experimental program, we in total have 11 walls, and we do have quite a few parameters that to be investigated. Including the shear span ratio, so from low walls to high walls, axial load ratio, anti-buckling stirrups, reinforcement layout distributed and the lump time distributed, and the end zone reinforcement ratio here, bar diameter, and the end zone length. So it can represent quite a few lateral reinforced concrete walls. And if I draw this wall tests data, in the picture that I just showing you of the database of the lateral reinforced concrete walls, our data is in here, which can represent a range of lateral reinforced concrete wall designs in multi-story buildings. So you can see our shear span ratio is 4 and 6, like most of the walls. So it can represent the multi-story buildings in many countries from the low to moderate seismicity. So these are the test data that we make up. And this is also the reason that why we do this test. And so this is a test overview that showing you the setup. So basically, this setup applies to every wall in the test program. So basically, we have three actuators, one horizontal actuator to apply horizontal force, and a pair of vertical actuators to apply axial load ratio, axial load, and the bending moment as well. So the bending moment on the top for this wall is to create a higher shear span ratio where we can simulate the multi-story building walls. And we also have quite an amount of the sensors that monitor the global and the local behavior of the walls. So talking about the data set that we collected the data and the documentation quite carefully throughout the test program. And mainly it can separate it into test preparation, pre-test inspection testing, and after test. So we collected the data carefully, trying to make the data complete as possible, and make the data high quality. So in next few slides, I'm going to describe what's the data, what's the steps in each stage, and what kind of data we included in this data set. So in the first stage that we have the test preparation. So this stage is a relatively long process. Probably took us several months to do that, but the documentation is relatively light. So especially for the design, we need to consider everything before we doing the construct. So it's kind of the iterative way. We need to consider about the setup, the instrumentation, the construction as well. So this stage takes quite a long time. And the specimen, and so the documentation that we get is the specimen drawings that for each wall, the test setup for the test program, and the instrumentation plans, and which we collected this a little bit detailed in a spreadsheet, like including drawings, the functions of each sensor, the positive direction of each sensor, and the calibration factors as well. And next stage is the pre-test inspection. So this one is takes maybe a couple of hours before testing. The main thing for this is measure the as-built dimensions and check everything is going well. So when we measure the as-built dimensions, for example, we need to measure the as-built instrumentation. So usually we will have a target or designed instrumentation positions, but usually when we install that, it's got some errors. So before testing, we need to record them to have an as-built gauge length. So when we interpreting the data results, we should use the as-built gauge length. Then we calibrating the camera positions. So we use photogrammetry throughout all our tests. So we calibrated the camera positions. So we got the calibration photos as well. And we do have initial damage checks before testing. So to see if there's any initial cracks or damage to the wall. And so we also record them and form the initial inspection notes. And also we check the sensor is working before testing. So the third stage is about testing. We usually took about 2 or 3 days to test one wall. And of course, the main thing that we do during testing is the sensor recording and doing inspections. So this test process actually forms the main documentation or data of our data sets. So first, of course, we will have a loading protocol. We will have a target loading protocol for each wall. And they are same, but for every wall that they do have some different loading protocols for each other. So we collected this loading protocol documentation for each wall. And of course, we have load sensor data. We're taking lots of photos, the loaming photos, global photos, sometimes videos as well for each wall. We mark the cracks and measure crack width at peak drift and also residual crack width as well. Throughout the test, we doing the observation notes. So we recorded the key phenomenon of the walls, including cracking of the wall, including vertical bar buckling, concrete crushing, bar flexure, and this kind of key stage that we keep records of them. And we also have the records for sensor availability. So sometimes when the bar buckling happens or concrete crushing, that the sensor never works again. So we take a note of that, and we know that the sensor is not working at that time, and we can't use the data from that stage. We are also doing, at the same day of the concrete of the wall testing, we are also doing the concrete testing. So we also have a documentation for concrete properly as well. So this is kind of the rule of the inspection during test. In each drift, we will have do 3 cycles for the wall. So at the first and the third cycle, in the inspection cycle at peaks, we're doing inspection of photos, loaming photos, global photos, and we also mark cracks and measure peak crack widths. But when the force is unloaded to 0 and 0 displacement, we only do the global photos and the residual crack widths. So this diagram actually helped me not forget the things. So it's quite useful during test and can help us to get the data, all these sort of photos and the crack maps as complete as possible. This is a camera plan that we do. So this is a plan of the setup. We have 3 cameras for monitoring the global behavior of the walls. So one camera with the whole test setup and the specimen, and the other 2 cameras measuring the 2/3 of the wall and also doing the photogrammetry. And we use DigiCam control software, controlling it in the computer. And we also have 2 GoPros to monitor the damage progress at the wall base at the angle view. Of course, we have a loaming loaming camera that we taking photos throughout the test. Yeah, so after the testing, we also did a bit of work. Most of the things that we do is we editing photos, taking photos, and rebar testing, and also the sensor data processing. So after test, the further thing we do is we remove all the gauges. So we take the final condition photos for the walls. And then we are editing lots of the global photos that we taken during the tests to editing this time-lapse video, show the deformation pattern of the wall and the whole process. of the test. Also, we're doing the rebar testing afterwards. And then we're doing the sensor data processing. So because I said like for one test, we usually take 2 or 3 days. So the raw data usually have separate files because the deck is stopped and we start again. So the first step of the data processing, we combine all these data files together into a single file and rename the channel name corresponding to the instrumentation plans. So we know each of the sensor name and then which is which. And then once we have done this, we filter the data and save the data into a MATLAB file and a TXT file. And we know that the history curve data is actually quite useful or quite a common use for people. So we extract the global displacement of the wall and the wall-based bending moment, calculate the wall-based bending moment. So we separated this data into a separate process data file, history curve. So in total of the process data, we have a history curve data, we have test data in MATLAB file and a TXT file. Yeah, so talking about these both stages and the documentation and the data that we collected, I created a few photos or files that where we can put all this documentation inside and make it clear that these photos and files apply to each wall and organize them into these photos. You know, for example, crack maps, we install for crack maps and crack weights, peak crack weights and residual crack weights, instrumentation for design the instrumentation and as-built instrumentations. Loading protocol for designed and the actual loading protocol for each wall, medium, you know, photos, videos, time lapse, sensor data for load data, for process data, for the sensor availability spreadsheet, test observations, material tests for concrete and the steel properties and more details and test setup. And we also have, I also wrote a README file which explains the data sets and my thesis as well to supplement explaining this. So after I collected all this data, I will tag them into the DesignSafe structures. So this is kind of a DesignSafe categories that existed in the DesignSafe. So usually the DesignSafe will have a overall project. And under the overall project, you can create different experiments under this project. And under the experiment level, we will have like model configuration, report, analysis. So model configuration is usually describing a specimen or a test program. Report explain the experiment or the whole project, and analysis is for interpreting the data results. So under the model configuration, you will have two categories. One is the sensor information that you put the instrumentation the information here, and the event that is the data generated during test. So according to this structure in DesignSafe, I create our own data set for the lateral reinforced concrete wall. So we create a project, University of Auckland lateral reinforced concrete wall tests. And under this, we created two experiments. One is the phase 1, current design, and another is phase 2, modified design. So under these two experiments, we have two reports. You know, one is the README file I just described, and the other is the report for my thesis. And then we have 6 model configurations for phase 1 experiments and 5 model configurations for phase 2 experiments. So this is kind of the overall structure in the DesignSafe that we stored. If you look at the DesignSafe structure, we separated, you know, phase 1, phase 2, and we have the 2 reports and the module configurations C1 to 6 and M1 to M5. So within each module configuration or each wall, we have tagged our photos or files into this. So under this, we have the sensor information label, and then we have the event label. I think it's quite obvious that we take the instrumentation photo into the sensor level because this is for instrumentation, and we tag the things that to the event and the model configuration we defined like this. So the data that we target into the events is the data that we generated during test, and this data can be used to interpret the work behavior. And this data we tagged into the event label. And the module configurations, the documentation or the photos we tagged here is that describe the specimen or the test program. So these are the three labels that we tag our photos and files into it. And hopefully this can be easily found. For example, for sensor data, medium, photos, videos, and time lapse and crack maps, test observation, that is to interpret the work behavior. So we tagged here these ones. And for the loading protocol, material properties, and more detailed test setup, we tag it into model configuration here. And the instrumentation, so of course, we tag into the sensor label. So if you look at the DesignSafe here for each wall, that we have this sort of model configuration, sensor information, and the event. And hopefully we can easily find it. So if you want to find the process data, you click the sensor data here, and you can easily access the history curve. You can plot that. Then you also can get all the data that from that instrumentation photo, corresponds to the instrumentation plane. And of course, if you plot them, you will need to look at the as-built instrumentation dimension that we measured before test. So these ones are some examples that I have plotted, using the data that have been included in the instrumentation. So reinforcement strain distribution, the curvature distribution. You can also plot the deformation contribution of each level of the wall, the wall elongation, and the plastic hinge length. So you can plot other things, use the data. So this is another example for when if you want to look at the crack maps. This is also in the event. You can click the crack map, and then you will find all the crack maps that are showing you. And you can also plot them, use this crack width, the height of the crack that to put it into a diagram and to quantify the crack width and the crack maps. This one showing you how do you access the medium. You can access the medium, and you can find all the time lapse for the walls. You can find the videos there, and also the failure modes for each of the walls. Yeah, so that's about the data set and just a bit of the summary. So the 11 wall scale represents the lightly reinforced concrete walls in many countries in low to moderate seismic regions. And we're trying to make the data set as complete as possible and high quality. So we collect the data quite carefully throughout each stage. And the data set is structured in DesignSafe category, and hopefully it's easily to be reused and found. So we have 3 journal papers that have been published related to this experiment program. We have a data paper that I just talked about to explain this data set. And then we have 2 journal papers corresponds to phase 1 and phase 2. So these 2 papers are explaining the data results and interpreting the data results. And this data set is already have some applications and impact to the real engineering practice. So the experimental result is being used to justify the modification of the minimum requirements in concrete standard in New Zealand and in the United States. So the key of the key modification of these 2 standards is that the previous version of these 2 standards, they only require the distributed reinforcement. And then in the current version, according to our test results, they have required that both require distributed reinforcement in the wave, and also the lateral reinforcement at end regimes. And this test result can, I think it can continue to impact the applications like performance design, like continue to revise the standards as well. Yeah, so all right, so next part is Rick's. So I'll hand it to Rick to introduce a quick core and the other test data.
Excellent. Yeah, so I guess looking at what we've done in that example, sort of reflecting a bit on why we were interested in doing it, and particularly some of the other data sets we've collected. And it comes back a lot to this Quake Core, which is our New Zealand Centre for Earthquake Resilience. And we established this sort of with some of the momentum from Canterbury earthquakes and a lot of the research that had been initiated from that, and that really brought together this multidisciplinary group of researchers to focus on really delivering good outcomes for us in terms of improved earthquake resilience. I think as we did that, we sort of perhaps found opportunities to really try and bring together data from across lots of researchers in New Zealand and internationally as well. And in my particular, I think thinking back that 10 years ago when we were collecting data from the Canterbury earthquakes, we really didn't have a very coordinated plan of how we did that. And I think a lot of the sort of reconnaissance data still sits on people's hard drives and photos here and there, but we weren't very well prepared in terms of archiving and making use of those data sets so that we could really share them and reuse them. And so I think there's been quite a good effort to do that. And certainly the RAPID facility is a great initiative to sort of try and get better quality data from some of these perishable sort of events as well. And the others in the experimental space that we've been doing lab tests for a long time, and anyone who does lab tests knows that they take a whole lot of time and money to do it. And yet in many cases we get the results, we use it, we publish it and do what we want, and then it sort of disappears. And finding old data from projects even more than 10 years ago is really quite challenging. And that leads to sort of trying to digitize data from publications and things, which just seems really somewhat pointless in terms of what we're trying to do and making use of that. So I think we sort of use that as a way of really pushing to try and collect better data and to really make sure we maintained and archived it and published it. And I guess that's where DesignSafe came in, and that New Zealand's a pretty small country, and there was no way we're going to establish some cyber infrastructure that's equivalent to that to do it ourselves. And even if we did, we probably wouldn't have the reach to sort of get visibility on that. So I think it seemed a really logical partnership for us to work with DesignSafe to publish these data sets and other data sets from our research into this platform. And that's really been quite successful, I think, and seeing quite a good increase in the number of projects doing that. Within the experimental facilities in Quake Core, we had quite a big push to sort of improve the sustained capacity of our testing in terms of the way we did things. And a lot of that's been a real drive to increase the quality of how we do experimental work, but also the really more systematic collection of data and publishing that data, like I said, to make it useful beyond just the sort of initial research that we're doing and getting our initial sort of publications and outputs out. So I thought I'd just go through and show very briefly some of the other data sets. So like I said, we have done quite a number of projects around concrete wall behavior since the earthquakes. And so we've also published another data set on some sort of reinforced concrete walls with higher axial loads. So these were sort of walls where we detailed them to current design standards using sort of ductile detailing practices and some of the recommendations following the earthquakes, and really wanted to assess higher axial demands and their capacity. So we're able to push these through to failure in an axial sense, which you see in the video, and gain a really good understanding of that. And combining that with other wall tests that have been done around the world and data sets and things has allowed us to really evaluate design provisions and look at deformation capacity and some of the detailing requirements for these walls. Going back in the other direction, we've also done some work on older singly reinforced walls, so sort of non-ductile type detailing. And this is a project which not quite published, but almost ready to be published as well. And so that was looking at these walls where we just have a single layer of reinforcement and quite poor detailing. We talk about it being older walls, but actually for a lot of lower seismic regions, these are still quite common in new buildings as well. And again, we were perhaps more interested in these tests in axial failure. So we're able to take these through to an axial failure and look at the capacity of that and some of the sort of vulnerability of them in terms of collapse potential. We've also done quite a lot on precast walls. So in New Zealand, we have a really extensive amount of precast wall tests that we have to do based on the practice that's sort of applicable in New Zealand. So these are some tests of grouted connections where we've published this data just recently as well. And the precast walls that use a common grouted wall to foundation connection where the starter bar is sort of grouted into a duct in the panel. The earthquakes that detailing had some vulnerabilities, in particular sort of loss of concrete around the splice or connection region. And so we did some work that helped to sort of refine the design of them and providing some additional transverse reinforcement to provide confinement when needed as well. Then more recently, we had a really great opportunity to do a larger collaborative test. And so this is another data set that we're just about to sort of publish, and it relates to a project we did between QuakeCore and ILE, which is a joint research center out of Tongji University. And we had the opportunity there to do a two-story building test that sort of implemented concrete walls designed for lower damage, so post-tension concrete walls. And these are representative of some of the buildings we're seeing built in Christchurch and places around New Zealand. And I guess for Icha and I who worked on this project, it was really another scale in terms of really systematically thinking about how we collect and sort of collate and archive this kind of data. And I think doing larger projects gives us much more appreciation of how we actually do that in a really well-organized way, and to make sure the data is really set up to be reused. So this is a sort of series of tests. Oh, I think it dropped out for a second.
Yeah, Rick, we lost you there for probably about 30 seconds or so. You were showing the picture of the two-story building, and we're probably about halfway through talking about that when it froze.
Excellent. All right. So let me just jump back. Yeah. So the two-story building data set here is almost ready to be published, and I think really provides a good opportunity to share something that took a lot of time, and I think the data is really useful for other people to be able to reuse and make you know, more use of it than we could potentially do ourselves. And the last project was just another collaborative project between QuakeCore and Taiwan. So this was my colleague Professor Ken Elwood and Shizhen Huang from InCrete, where they did the 7-story building looking at torsional irregularities and using the shape table in Tainan lab to do some really amazing experiments of that as well. And that's all been published and available for people to use as well. So I think sort of some thoughts to finish up. Really this idea to me that experimental data should always be published is kind of becoming the norm. And I think we're really trying to ingrain that in our process, that It's not just about doing the test, it's about actually using that data and publishing it for reuse. I think we're seeing that the publication of these data sets and data papers is really quite a valuable academic output, and I think DesignSafe's been really a great advocate to sort of promote that. And I think we've learned quite a lot from trying to understand how to do this well, and so I think it's important to sort of share experiences and lessons of how we do this, and perhaps get some more consistency in the way in which we publish data sets. Particularly with the way we do tests and what data we collect. And that sort of just allows us to keep improving the quality, perhaps collecting data that we don't necessarily need ourselves, but that could be useful for other people, and it's not too difficult to sort of add in there. I think we're sort of confident that we're publishing things from what we know, but I guess the uncertainty is that other people who might want to use it, we don't really have a good idea on what they're going to do with it or how they want to see the data. So perhaps in time we'll get a better understanding of what sort of reuse tends to be, and that might also help to impact some of the sort of way in which we publish things in future. And lastly, really just a thank you to DesignSafe. I think, like I said, it's been a really valuable opportunity for us to be able to use the DesignSafe platform to publish this data, something that, like I said, we wouldn't be able to do ourselves as a country in New Zealand. And I think it's been really successful in terms of providing a central point for this natural hazards data to be published and really visible for other people to go and easy to use. So always been very helpful when we're trying to publish these data sets, and really appreciate the support and partnership that we've had via QuakeCore as well. So with that, thank you, and thanks for joining into the webinar.
All right, thanks very much, Rick, and you too. I think as we wait for questions to come in through the Q&A, feel free to type your questions in the Q&A if you have them. I do have a couple. So first, I'll just say, Rick, you mentioned that it's a lot of work to gather these data. I'll add that it's a lot of work to organize it and curate it in a way that makes it reusable. So thanks for your effort there. It's a really well-organized data set that you've put in there, and well worthy of the data award. A couple questions I had, you showed those crack maps, which I think were in a PDF format. Are those data also available, and do you foresee a data reuse opportunity with those crack maps, maybe combined with some of the images that you gathered? You took photos of the walls at different places, like mapping the image to the measured cracks and things like that too?
Yeah, I think maybe each you can add, but these are tests that were quite a long time ago. So I feel like we're improving, and perhaps at that point we were doing hand-drawn crack maps and scanning them. More recently, we've been doing a lot more crack mapping on, trying to annotate in AutoCAD to get digital crack mapping, which is a bit easier to use and sort of keep track of crack widths and things. But also I think something that we've played around with, but not necessarily, got very complete output, but using digital image correlation and things to actually generate additional data on sort of the visualization of cracking and width calculations, rather than the manual measurements we do, may eventually sort of make some of that data collection not necessary, and speed up some of the automation and the way we can do that. So I think, yeah, integrating the data is probably something that we need to keep improving.
And I had one more question too. DesignSafe also has some simulation tools built in, like OpenSeas is there to run. And I was just wondering if you're aware of anybody reusing your data to calibrate wall models in OpenSeas or anything like that to try and refine their modeling approaches, or whether you've done some of that work yourselves.
Yeah, I guess I'm not aware of anyone necessarily having used the data set yet. Maybe if people do, it'd be good to hear people's experience, but I think we certainly hope that would be one potential use. And OpenSeas modeling that we've done, we certainly use those and other published sort of wall tests to calibrate and validate models and things as well, and have had quite a few students doing OpenSeas modeling using some of the DesignSafe tools and the platform there as well. So I think, yeah, sort of integrating some of that across the tools is something we're looking more at as well, rather than just the pure publication of the data.
All right, great. So a question did come in. It's more just praise. Many thanks for your efforts and excellent presentation. So nice job.
Thank you.
And Charlie, I guess I'll turn it back to you at this time.
Sure. I just wanted to echo Mohammed's sentiments. Thank you very much for your efforts. That was a really great data set, and it's very cool to have that sitting on DesignSafe. I would like to actually say as well, for those of you who are in the participants, if you have data that you would like to upload to DesignSafe and share with the rest of the community, please do so. If you have if there's any help that you require to get this data into DesignSafe, or how would you categorize your data, there is open office hours that Maria, one of our data scientists at TAC, she runs these office hours on Tuesdays, I believe, and Thursdays, I believe. So please come in and talk about your data, help, and have Maria help you get your data set hosted on DesignSafe. So there does seem to be a question in the Q&A that just came through right now from Mohammed. He goes, have you assessed the out-of-plane action of the walls as well?
Yeah, good question. I think the tests that we've done are only in plane, and so they weren't assessing any bidirectional demands, and the lightly reinforced walls are not very susceptible to out-of-plane instability or buckling when you get concentrated cracking. But we did have a project led by one of my colleagues in Canterbury, Professor Rajesh Ductile and Stefano Pampinen, who had a student looking at some of the out-of-plane instability. And so they did do a series of tests looking at sort of in-plane, out-of-plane instability and in-plane demands, and also some bidirectional demands as well. So I think they're certainly hoping to get those tests published as well, I think, and that'll be a good addition to some of the data available.
Thank you. All right. So if you came in late to this webinar, or if you're interested in some of the other webinars we've hosted at DesignSafe, you can check out designsafeci.org, our learning center /training from the main DesignSafe page. We have an archive of all of our DesignSafe webinars, as well as a link to our YouTube channel where those webinars and some quick guides are hosted. With that, we appreciate your feedback. There's that QR code again to be able to fill out the DesignSafe survey, so we can prepare better webinars for you in the future if you'd like, something more concentrated or anything that you're wanting to learn about. And once again, thank you very much to Rick Henry and to Yuki Liu. I know it's really early where you guys are located at, especially Yuki. It's about 4 a.m. when you came online with us. So thank you very much for your time and your efforts on this. Thank you for presenting your data sets with us. If you have any questions on this webinar, there is a Slack channel available for that. You can ask that in the general Slack channel, or you can email us at training@DesignSafe, or fill out a DesignSafe ticket. Once again, thank you very much, everybody. I hope you all have a great rest of your day. Thank you.
Thanks.
Yeah, thank you very much.